Well, welcome. Thanks for coming to my talk. So after Jonathan's talk, this is going to be a really practical talk. This is a really practical talk on how to program. How do we program in C++? We all want to reuse code occasionally because we are pretty lazy as programmers. We are lazy, and that is a good thing. We don't want to repeat ourselves. In fact, this is so important to us that we gave this a fancy name. We called this the do not repeat yourself principle. So we want to reuse pieces we've written for something else in other locations of our code base. But of course, I'm joking, it's not just laziness. This is an aspect that is critical for maintenance, for achieving software that is easy to maintain. Because, well, if you don't repeat yourself, then you only have to fix bugs once and not in different locations in your code base because you've copy-pasted code all over. I want to look at the strategies we have in C++ to share algorithms and sometimes data. I want to give some guidance on when to use which. So why am I giving this talk? Well, we have a lot of tools in C++, a lot of fancy tools, and we like to give a lot of talks about those tools. But we don't give a lot of talks about when to use which tools. And in fact, I'm interviewing a lot of candidates for open positions. And my interview obviously requires a bit of programming. And time and again, I see especially junior developers choosing very, let's say, suboptimal ways when they're tasked to refactor a bit of code. So that's why I wrote this talk. It's the first time I'm giving this talk, by the way, in front of an audience, so I'm happy to hear all your feedback afterwards. Okay, let's start with a small example. Let's say we have a super clever layout algorithm. And that layout algorithm can center widgets vertically. My slides are in HTML, so you know that centering stuff is actually super complicated. They have different shapes, so we, for simplicity, will just place them by their, or lay out them by their bounding boxes. So we might have an algorithm that looks a bit like that. It's called vertical center, it's already a very good name, and it takes a container of those things. Now, all my code samples use our ThinkCell open source library, but the code examples are always pretty short, so that should be easy to follow. So first of all, we're creating a vector of all those bounding boxes, of course, that we want to center. Then some magic happens. And then afterwards, we go over all the widgets and the rectangles, and we place them where we want them to place. So let's say we have now a slightly different problem. We have rectangular bitmaps somewhere else in our code base. They're not widgets, have no relation at all. They just happen to be rectangular things, and we want to use the same algorithm because it is a clever piece of technology. Now, how do we go about that? So we have a bit of code, we have this array of those things. What do we do now? We need some data structures for completeness, maybe. So the widget had those two member functions. It can output a bounding box. You can place it somewhere. And the bitmap is something completely different. It's just an array of bytes, essentially. It has a width and a height to make sense of those bytes. Otherwise, well, these types have nothing in common. And now, when people see similar problems, let's say, so I didn't want to show too much wrong code on my slides. So I chose the least wrong solution to show. When people get a task like this, a lot of them, of course, see, hey, I can reuse code. That part usually works well. And then they also see that maybe we can make this function into a template somehow and then reuse it. And we can call it with something different. And then they stop and they say, cool, problem is solved. I'll just give my bitmap somehow the same interface of that thing I put in there before. I somehow, well, built this contraption just for that simple use case of reusing code. And of course, that will work. You will get this to work, and you will solve this problem. And if, well, solving a problem is your only metric, then of course you have achieved some level of success. But if we're writing large-scale software, then that's not our real measure of success. We want to do better. So people usually see that code can be reused. That's our laziness kicking in. And then the laziness takes over, and the first instinct is to not change anything. Ooh, there's this complicated piece of code. I'll not read it. I'll just give stuff same interfaces, and then magically, by using templates, things will just work. Because understanding code is super hard, and writing code is very easy. Writing code is fun. That's what we're paid to do. Making stuff work is fun. That's why we probably chose this profession. And the more tools we know, the more bad ways there are to make things work, unfortunately. We could have shared the code by passing in a variant of either a bitmap or a widget, by building an inheritance hierarchy. Well, that's essentially what we did. We could have given them virtual functions for some reason. All these things would have worked. And what they all have in common, of course, is that we are fitting this square peg in a round hole. But when code reuse is critical for maintenance, then of course it is also critical that we find the easiest way to reuse code. If we build contraption upon contraption and we make more unnecessary code, maintenance will get harder and not easier. And we want to make reuse easier. So what's like the 10,000 feet or meters way on how to reuse code? How do we think about that? So of course, we first have to understand our own problem, the new problem. What is it that we need? And then we have to understand the available algorithms. What do they do? And then we have to describe both in terms of the actual problems. And that's maybe the crucial part here on that slide, and not C++ jargon. So when I ask people in interviews, can you describe what this does, what this code does to me? Well, their always answer is, yeah, this calls this method, or this creates this type. So they answer in C++ lingo, and they never describe the actual algorithm. But only when we can talk about algorithm in terms of the algorithm, we can generalize and find good solutions that enable us to write generic reusable code. So how does that look in our simple example here? We have that bitmap, like I said, doesn't have a rectangle. And we have this algorithm. And when we look in this algorithm, of course, that is easy to see. We see that it's really operating just on rectangles. Doesn't have anything to do with widgets, really. It's just transforming rectangles, somehow doing some calculations. We could analyze this magic further. Maybe it turns out it doesn't actually operate on rectangles. Maybe it's only operating on intervals. That's what we have to analyze the algorithm for. But let's say now for simplicity, it's really doing some calculation on rectangles. Then of course we should write it that way. We should rewrite it, refactor it, and say this is an algorithm that is really operating on a range of rectangles. And here for simplicity, I say that this is a range that returns references to rectangles. So when we do this, code becomes super easy to reuse. We can maybe do some simple initial calculation for these rectangles and then call a function operating on rectangles. Not necessary to build any contraptions. Because what we've achieved by this little transformation is that we've written, or we found a function that requires only very minimal concepts. It's more generic, it's easier to reuse, has very little dependencies. It doesn't depend on widgets anymore. It just depends on the things that are inherent to the algorithm that we have. Rectangles, essentially. So that's my first point. A very well-known point, I hope. So when we have a shared algorithm and we want to reuse it with different data, then the tool that C++ gives us for that is a generic templated function. And we write good generic functions by extracting the minimal required operations, the minimal operations that are required on our inputs. And we describe them as concepts. Or better, as Bjarne Strostrup says in a paper that I think was titled How to Write Better Concepts or so, he says, instead of extracting minimal concepts for each new generic function, it's better to come up with a set of reusable fundamental concepts that become well known, that you can use in many places. Or let's say regular type, for example. In order to come up with those concepts, we have to analyze algorithms. We have to understand them. We can't just blindly reuse them. And of course, as always, it's a bit hard to generalize from a single use case. So we might only do this if we have actual reusable, well, if we actually want to reuse stuff. Now let's quickly revisit some patterns that we have to write good, flexible, and powerful generic functions. Because a pattern we often have in our code is that we have some client code that wants to call some generic function, and that generic function should call back into client code to do stuff. The first pattern we have are function overloads. So here, stay a bit in the same problem domain, something to calculate, and I call this place items function with two different vectors, and calculate rectangles again. And what the function does in the end is it's just calling a global place function. And this global place function now has to exist as in, well, overloads have to exist for the input types that I provide. That's a very elegant way to customize generic function. It doesn't require any boilerplate code. The compiler does everything for you. It's also non-intrusive, which means that this works for any types, not just for types that you control. You can provide overloads for ints, for std strings. And the one disadvantage is that maybe the contract is not quite clear to the caller, right? So you have to take extra care to document that you expect this global function to exist. And this is, of course, something we do all the time in the STL. So there are std size, std begin, and std end overloads, for example, precisely because we wanted to customize them for built-in C-style arrays. The second way to generalize, to customize generic functions are output functions. So output functions are similar to output iterators. Output iterators are very frequent in the STL, but output iterators are kind of a weird concept because they're not really a minimal concept. You can assign stuff to an output iterator, and for some reason you have to increment it, when all you wanted to do is calculate a result and pass it to something. And that's what an output function does here with an invocable concept in the template arguments. And this is a very flexible extension mechanism because we can write output functions that perform allocations. If an allocation is what we need, if we want to gather this data in a vector or something, an output function can do that. But for a lot of algorithms, what you really want is you want to immediately process data, of course, and you can do that in that output function as well. And output functions are especially cool for algorithms that calculate their results bit by bit or piece by piece. So let's say, again, you have some layout algorithm that is, I don't know, calculating positions from the top to the bottom for rectangles that have different height. Now, of course, you can only calculate positions after you've, let me rephrase that. You can only calculate the position of the fourth item after having calculated the height of the previous three. So the results come in bit by bit, and you can output them immediately, and then, for example, immediately draw them. Okay, we can pass other functions, of course, other function objects. That's something the STL does a lot. There are different types of function objects in the STL. Predicates are one of them. Projections are other function objects. Projections are function objects that are accessors from, let's say, your range value type to some other type that the predicate can then operate on. Again, function objects are very flexible. They're more flexible, let's say, than requiring that your input arguments have specific member functions. That's not a very flexible concept. But you can imagine that when you have very special, complicated algorithms, putting in a lot of function objects in your argument list becomes quite kind of difficult to understand. So we can do one last thing to make things a bit easier to understand. Again, we can adapt the so-called command pattern for generic functions as well. So I'm changing the problem I'm describing. Let's look at dynamic programming. Let's say we have a generic dynamic programming algorithm that we use, for example, for calculating the edit distance between two strings. So this dynamic programming as an output calculates a vector of matches, and you input two ranges. And now this algorithm has a lot of customization points. So we can group them together to make the interface a bit easier to understand. So the customization points might be the type of the cost. Here it's an integer by default. The initial costs might be a customizable value. You have to provide a cost function that actually calculates costs of the next step. And when you customize the cost type, you also have to provide some kind of comparator so you can find the minimal cost path through your solution. And we group them all together to make this a bit easier, to make the interface easier to understand. Okay. So in summary, generic functions, super powerful. They need clear requirements that we express in concepts, but then they have limited or very minimal dependencies, which makes them great for code reuse. And they remain flexible, customizable, and very powerful when we make them customizable. Now, what do we do when we want to share some code and some data, like some state, for example? Because our dynamic programming example actually had both. It had an algorithm, but it also always has some data. That is the list of matches that we calculate. And data and code together, that's what object-oriented programming was invented for. So of course, we could put that dynamic programming example into a class. And now the class is called dynamic programming, and it's templated by its derived type. We can put in the cost function as a class template argument, and also the initial cost. The value we share between all instances of the data, is the list of matches that we will calculate. Now we can give that a nice generic interface because it actually turns out that we want to iterate over those matches back to front, the way this algorithm works. And now we have the shared code, the calculate function. And we derive from this, and I think you recognize this pattern, we derive from this and all the customization points are now in the derived class. So this is, of course, what's commonly called the curiously recurring template pattern. So the derived class is now our string matching instance, and it provides the cost object, the comparison function, the cost function, etc. So that's a very well-known pattern. And if naming things is the hardest part in programming, then we horribly failed on that one, because that's really a very nondescript name. Maybe it should have been called templated derived class or something like that. So when we share code together with some data, we can write generic classes. The curiously recurring template pattern, or CRTP, is one way to do that. So we're using compile time polymorphism to combine common algorithms and common data together into new customized types. So we have, for example, generic interface, generic algorithms and data in that templated base class, and customization points in the derived class. Now, if we can put customization points in derived classes, we can, of course, also put them in base classes. So let's say we have some process that we can pipe data to. And we want to customize how we do that. So we provide a base class as a template that will provide the fundamental operations that we need for piping. And we can customize this in different use cases. One use case, for example, is you want to customize the way in which you're writing, so here asynchronously or synchronously, and then you build a common interface on top of that. Another reason to do it that way might be that you want to you have different base classes for different operating systems. So the base classes, in all those cases, they hold different data. They hold different data, and then they implement a common operation on top of that different data. And usually it's practical to put data into base classes, so it's easily accessible. Like the CRTP pattern, the inheritance here is an implementational detail that is not actually really visible for the end user. It's just the way we combine types and code together to build new types. New colleagues, junior programmers often ask me, how do I decide which one to use? When do I use the CRTP pattern? When do I use templated base classes? And that's very hard to answer in general. It's usually a question of convenience, because we're talking about convenience here. How do we make code reuse as easy as possible. Questions I ask myself when I think about that is, who owns the data, for example? What's the initialization order I need for my data members? And that sometimes gives hints that, for example, like I said, it's more elegant often to put data in base classes and then put operations on top of that data in derived classes. But really, it depends, and the real answer is you do whatever creates less friction. This is not a huge design decision. This is just for making stuff. This is actually just for making stuff work. Now, when you have templated base and templated derived classes, you can also have something in the middle, mixin classes, of course. With them, we often add behavior to otherwise completely unrelated or relatively unrelated types. So let's say we have some UI widget that has a mouse move method. We have different UI widgets that derive from that, buttons, drop downs, whatever. And then we have a very useful mixin class, beep, that makes your computer beep whenever you move the mouse. So that's something everybody wants, and that we can now add to different widgets to make them extra annoying, even though they have otherwise little in common. Okay, any questions so far? No. So now you could ask, well, what about inheritance? What about virtual functions? I use them all the time. And yes, sometimes I use them to make code easier to reuse, to be reused. What about state variant? Well, I haven't talked about them yet, but I will now, because we don't use them to reuse code. So code reuse is an implementation decision. It's something we do, like I said, out of convenience. We have different parts that all call the sort function, but that doesn't mean that those parts in our code base have anything to do with each other. They just happen to need a sort function. So we just don't want to repeat ourselves. And we can use generic functions or generic classes to encapsulate that functionality that we want to reuse. We reuse code in unrelated contexts that doesn't tie them together. And like I said, out of convenience, not because that would be a huge design decision. Inheritance or runtime polymorphism, by contrast, that's a design decision. That creates a structure that has implications for your entire code base. So that's something that, well, we should think a bit about before we decide to model our problem using runtime polymorphism. It creates a strong coupling between all the types that are part of that hierarchy. They now all share the same base classes. And that common interface the base classes provide. So this interface must have the same meaning for all types in your type hierarchy. And even worse, the implementation you provide must be correct for all those types in your type hierarchy. And we've probably all seen cases where that was not quite the case, where suddenly somebody introduced dynamic type checks for saying, is this really one of the types I want to be calling this method for, or would this not work? There's this famous talk by Sean Parent about runtime polymorphism. There are two versions of the talk, and the shorter one has this famous title, Inheritance is the root class of all evil. And he talks about runtime polymorphism, about its disadvantages in those talks. Runtime polymorphism means that you have types, you build types that have different size. That means you now require heap allocation to create those types and hold them. Heap allocation means you have to do lifetime management. That means you're getting an inefficient indirection. It encourages shared ownership and then leads to synchronization issues. And in his talk, there's this famous quote that the requirement of a polymorphic type, by definition, comes from its use. There are no polymorphic types, only polymorphic uses of similar types. And that means if you don't have any place in your code where you're having polymorphic usage, that means you're calling some function without knowing exactly on what type you're doing an operation. Then you don't need runtime polymorphism at all. So let's look at 3 different ways to use runtime polymorphism with very different advantages and disadvantages, depending on concrete use cases that we might have. So maybe the classic example is you are something like a drawing application. in our case, think so. So the user can add stuff to your document, and from the point of view, very different things. And from the point of view of your document, you don't care which one it is. From the point of view of your document, they're all the same. They're all rectangular objects that can draw themselves, that can be selected, that can be dragged, that can be deleted, that can be grouped, that can be saved, that can be resized. They have this enormous interface in common. So this is maybe one of the canonical examples I can think of where using runtime polymorphism in the standard object-oriented way is probably an actually good idea. Because you have this object-based class, and it has some common properties that they all share, and it has a huge set of virtual functions. Every object can build a context menu, can react to a context menu click, and can then draw itself. And the document itself would just hold whatever objects the user adds. It doesn't even care. And practically all accesses, all usages of these objects will be polymorphic usages. And yes, they would be all heap allocated, but for example, other things that Sean Parent mentions in his talk, and I would recommend you watch his talk if you haven't, are not very relevant criticisms here. So he says that runtime, the polymorphic type hierarchies are hard to extend, but this is not a library, this is the core of our application. Extending this is hard for other reasons, because it involves a lot of programming, not because of the inheritance. And so other things like type hierarchies being intrusive, etc., they don't matter that much either. But this is different in other use cases. And there are different compromises we can make. Let's say we want to implement a UI library for maybe writing nice user interfaces like this I dreamt up here. So we have a user interface library, and that user interface library can automatically lay out dialogues. And that means there is actually some polymorphic usage. So you have maybe every widget, for example, needs to support some kinds of constraints. So all widgets have some interface in common. They all have a minimum size. They can all calculate some constraints so they look good, and set them in a solver. And when you have a solving result, they can all place themselves at some rectangle. And then you have different widgets, again, that will implement this slightly differently. And you also have a generic dialog, and that will also have a lot of polymorphic usage of its widgets. When it's resized, for example, it will simply collect all constraints over all the widgets, will solve it, and then place all the items again. So okay, check. We do have some polymorphic use. But now look at the user side. How does a user use such a library, such a dialog UI library? Well, we want to use it like this. We have our own simple dialog, and that has, in this case, just a text box and a button. And these objects have a clear identity. They are not just things in a big bag of dialog widgets. This is my text box, and I want to ask it, what text did the user enter? And this is my button, and I want to set event handlers on it, or change its text, or whatever. So these objects have clear identity. They also have a clear lifetime. They should just live with my dialog. When they die, they die. I don't want to reference count them, or any crazy thing. So how can we get those two things together? We want to have a bit of polymorphic usage in the dialog. We want to have simple members in our dialog with clear lifetimes, clear identity, etc. We could do something like this, for example. We could provide a virtual visit function. And that visit function would have to enumerate all our dialog widgets. Now that's clearly not a great idea, because it means that we have to repeat all the members again, right? Super error prone. No compiler will warn us if we forget one of our members down here. This will just silently not work at some point. So instead, we can do something else. We can use intrusive lists. So boost intrusive is an implementation of an intrusive list. Who here has used, or who here knows what intrusive lists are? Or intrusive containers in general? Okay. So intrusive containers are containers that don't have ownership of your object. So your object lives somewhere else, but it can insert itself into that container. And that's, in this case, super practical. So we change our dialog widget a bit, and our dialog widget will now have a base class that just contains the data structures the intrusive list needs. If that's a list, then it's probably just 2 pointers. So we carry around those 2 pointers with ourselves. And it has one other thing here, is this auto unlink in the end. That just means that when the dialog widget is destroyed, it will automatically remove itself from the intrusive list. Cool. Now the dialog has this intrusive list, and all that's missing is that every dialog widget registers itself when it's constructed. And then we're already done. We have objects with clear identity, just members in our dialog. We don't actually see this intrusive list as users of our library, but the library can itself build some data structure to get the polymorphic usage it needs. Cool. Without a heap, without ownership problems, without reference counting. Any questions about that? Yes? Sorry? They, I guess, write yourself an intrusive list. It's really, it's a linked list.
I think a similar thing as well, just sound better, but know that this part would be event that these may be pointing mainly on the vegetable. Just know these points. Is that a similar concept?
Sorry, can you repeat that?
So I've used in some cases where I've had a vector of pointers to the byte, but it's a better, but it's not good.
Well, vector would be impractical because it's hard to remove yourself, but a hash map of pointers would work. Then the dialog widget could remove itself elegantly from that hash map of pointers. That, I think, would also work. Yeah.
We're also using that list like register myself and deregister myself, full similar things like that.
Yeah.
So it just keeps on trying to think of ways that I can do it without roots.
Yeah. I mean, you can.
Relevant to me, and not knowing roots, I can't use that. So I'm trying to work out how to apply this to my own code.
Yeah, I think the one advantage that this intrusive concept has, and I mean, anything Boost has, you can do on your own. It's not rocket science. This is really just a linked list, but the difference is that the objects you put in that linked list, they carry around those 2 pointers with them. So that means it doesn't have any overhead, essentially, whereas having the hash map of pointers involves at least a little bit of allocation. Not much, but a little bit. And you don't have that here. That means you can only add them to one intrusive list, but in that case, that's all you need, right? Whereas you could add them to, theoretically, you could do what you do and put them into many hash maps. And then, oh, any other, yeah.
I don't really see where the button and the text box are now added to the dialog.
It's the dialog widget constructor that does it. The dialog widget constructor is just the base class constructor, and it always registers itself in that list. Right, the one that was highlighted. Let's say that always runs. I think I didn't, if I go back, that these text box and button constructors should get a reference to their own dialog or something. And then this constructor would do it. Right. Okay. So that's one way to use runtime polymorphism, the advantages, without some of the disadvantages. And Sean Parent, in his talk, gave another very interesting way of using runtime polymorphism that I want to, without the disadvantages, that I want to quickly recapitulate for completeness, because it's also an idea I hadn't seen somewhere else. So the use case he has is that he has like a document, and we want to add different kinds of objects to that document. So it's just a vector of those things. And then we have one operation for simplicity that's drawing this document, which just means to draw all of these objects. And now we want to have something that is easily extendable. So especially it should be maybe user extendable. So here we are just emplacing we're putting a 5 in that document or a string, and this should somehow work. And ideally, this should even work with user-defined types. So the simple classic object-oriented solution is that this object type would be the base class, it had virtual functions, we would have to derive from it, and then put in unique pointers of those objects into that vector. But that means that the user of that library has to fuzz around with those pointers all the time. And also it makes it harder to extend because, well, we can't inherit an int from object T or a std string. But maybe that's what we want to put in there. Now, Sean's solution is much more elegant, and he essentially hides the runtime polymorphism inside a value type. So we have this type object T. It has one constructor that takes anything and internally makes an allocation. It creates a pointer, of course, to implement the polymorphism. We see what this pointer does. But on top of that, object T will be a value type, movable, copyable, assignable, whatever. Now we're carrying around a pointer now to some base class, but this is all internal, not visible to the user. So we have maybe our concept T base class that has a virtual function draw. And the actual object that we allocated derives from concept T, carries around our data. This could now be anything, could be an int, std string, any data type you don't control. And now comes another cool trick. It implements this draw function. We do all the way. We implement draw on the object, go to the model virtual function that does a draw, and that dispatches to a globally overloaded function. So like in my generic function extension point example in the beginning. So for the user, this is now super simple. Yes, because the user can now put anything into the document as long as he provides those overloaded draw functions. So that's a nice trick to hide the runtime polymorphism that you need, the polymorphic usage that you need, hide it somewhere without exposing it to the user. For the user, this is much easier to use than an actual inheritance hierarchy. Okay, so runtime polymorphism is something that we use when the precondition is that we have polymorphic usage of stateful objects. If we don't have stateful objects, we don't need classes at all. And if we don't use polymorphic usage, well, we don't need polymorphism. So now we've seen 3 different ways on how to do this. If we have the standard object-oriented solution of completely interchangeable objects, we can just own base class pointers. If we have objects with identity, we can use intrusive containers. And if extensibility is important, we can hide polymorphism entirely using Sean parent polymorphism, so I would call it. Okay, now something fun. I brought some mistakes we did, because this is now a bit more about design. And design decisions are often complicated, and often they turn out to be wrong 10 years later. So I brought at least 2 examples where we did the wrong decision to illustrate a point I will be making. Let's revisit this document example. So we have this drawing application. Like I said, every one of those can render some user interface. So you see they're selected, and they have all these little drag handles that you're familiar with from any other application. And now 20 years ago, everything was still object-oriented. So of course, we implemented these in an object-oriented way because we thought this was the way to do it. And so the super high-level view of our application would have been like this. Our application would update its data model. The user made some changes. We propagated those changes. And then every object would create, for every drag handle, for any other UI object, it would create an instance of an object. So there would be a global list UI objects, a global vector of UI objects, and we would create a drag handle for every one of our corners, for example. And then later, we would get a mouse move. We would go over all these UI objects, call mouse move on them, and all they would actually do is to check, is the mouse over myself? And if the mouse is over myself, I have to draw myself with a slightly different hovering texture, right? That's something they would remember. That's the state they had. And then again later, we would get a draw call. We would go over all of these UI objects again, ask them to draw themselves, and then they would remember, hey, do I have to draw myself in the hovered state or in the non-hovering state? And now I said before, we use runtime polymorphism if we have polymorphic usage of objects with actual state. How many of those drag handles do have actual state? At any one time? One. One of them has the one that is hovered has actual state. Now it's a bit more complicated with things you can click, but that's still, you can also click only one thing. So that's still valid. So we later discovered that this was all unnecessary. Unnecessary runtime polymorphism, unnecessary objects, really. And the model is now much simpler and looks more like this. On mouse move, we essentially do nothing, set dirty maybe, trigger, redraw. And then later we get draw calls, the actual operating system draw calls, and they are implemented using a visitor. And every one of our document objects can now say, I have 4 corners. One of them is going to be drawing a different texture, and I'll just find out now which one that is. No allocation, no runtime polymorphism, no nothing. Just a visitor that does what it needs to do. Okay, finally, std variant. What about std variant? I've seen people use std variant for code reuse, but that's not what we have it for. So std variant is this awesome value type that we use to combine classes with that have no relation to each other, right? We can combine things that we don't even own, like std strings, for example. So we use it very often to return results that have different types. So let's say we're searching image databases on the internet, and we either get a result back or we get some error message. And now the superpower of variants is that we can do different things for those different results. So where the superpower of runtime polymorphism is maybe that you can do the same thing for different types because you don't care which one it is. Here you can have one type and you can do different things depending on what's contained in them. We do this by writing a visitor, and then maybe we can show an error message when we get, or we show an alert when we get an error message, or we display results when we get results. Okay, cool. But std variant, like std tuple, has a certain danger because it's almost too easy to use. It leads us sometimes, it's so easy to extend and lets us write or lets us invent ad hoc types, so to speak. So we extend it because maybe we're searching another image database. Now we have another result type. It's like because it sends back data in slightly different format. Now we change our application a little bit. We handle the error message super early, but we carry around those different result types for a while longer. Now we find code that looks like this. We have a download function. We download those 3 result types. Somewhere else in our code base, we have this function that's just downloading the previews for those 3 result types. And yet somewhere else in our code base, we have an authenticate function. So you see maybe where this is going. We used a simple variant that was easy to extend and extended it to such a degree that in the end, we actually reinvented polymorphism. We should have used, maybe should have used, a polymorphic type in the beginning because we've changed stuff around for so long that suddenly we had a variant with 3 containing types that all supported the same operations, and maybe we should have programmed it that way from the beginning. So as a single type that has 3 operations. Okay, so that concludes my talk. So we use generic libraries to maximize code reuse. And you should build your own generic library for each of your applications, probably. Abstractions, design abstractions, we have to choose carefully. And those different abstractions, and that's what my mistake examples try to show, these different abstractions are interchangeable, but these don't have the same costs. We can often exchange runtime polymorphism for visitors, variants for runtime polymorphism, etc. But only one of them will be the most elegant one, typically. And we have to revisit past choices that we have made, because very often our code has evolved a little bit. And what was originally a good decision turns out now to be the wrong one, and we should have refactored something a long time ago. Thank you. I have time for questions, I think. And as Jonathan also said, we are always happy if you want to work with us. And I still have socks for everyone who has a good question or feedback, as I said. Any question? Or comment? Or yes. Trades classes. Yeah, not that much. I think a little bit what I called the command pattern, I think you could have called trades classes, maybe commonly, is a bit like that, right? You customize some aspect of something, but you put everything together in one class. Yeah. Yeah, could have called it trades classes. Any other question? Silence. Okay. Didn't say anything provocative then.
And
Yeah.
I have one if nobody else is asking. In the last, did you say that the code evolved from using runtime polymorphism to variants?
No, in that case, it should evolve the other way around, but I still have to do that.
Okay.
We use variants and then it got out of hand, and then you wonder, when I add one more image service, how many places in the code base do I have to change? And then you notice that was maybe the wrong decision.
Okay.
Yeah.
Okay. Cool. Thank you.
Yes.
Your good idea is that to templated version.
Templated what functions? Templated virtual functions.
Looks like shit work.
Yeah, yeah. Now, what do you want to template? I mean, that's then typically, yeah.
I think you can't template a virtual function. You can have a virtual function inside a class.
Yeah, yeah, no, of course you can't. Yeah, yeah, that's his point. That's his point.
I need variables.
Yeah. Yeah. It goes a bit against what I tried to say with the runtime polymorphism example. Like, how generic is your virtual interface really for all types if you then call it with different types? I can see I can see the usage though, I guess, especially with the number types maybe or so. Yeah. Okay then, Molly, I'm still here. So if you have any feedback, I would actually be happy about if you had any comment. But you can do that in private.
One thing you just said that the variant has turned out to be an error, a mistake.
Yeah.
I wouldn't say so. The design has evolved, right? At the beginning, it probably was the right decision to use a variant because the problem was too small to just go full-fledged.
Yeah. Yeah.
And then at some point, it has evolved, and at some point, we have to make the decision, okay, now the old solution is not correct anymore, we need a new one.
But even then, I think in the moment somebody decided to have the variant of only result types, I think it went wrong that way. So because I would think that's the difference between the two cases, not how many you have, is that a variant is cool if you actually need to do different things for those two things, right? Even already, maybe the problem starts earlier. Maybe the problem already starts when you don't return the variant and then immediately process it, but you store it somewhere. Because then you will have a similar visitor in a lot of places in your code base. And that's maybe, I'd say always, maybe not such a good idea in general. Yeah. Okay then. Thank you very much for coming.